All right, for the second half of our problem solving session, I moved on to the third page of our worksheet from today. And I didn't write in all of the text, and I've included two of the structures. But the instructions say to draw an arrow to indicate the position where the major amount of mononitration will occur on these compounds. And then some of these questions in this packet make you think a little bit more and are asking you to explain why, types of things that will hopefully help you have a deeper understanding so that you can easily answer questions in either active or on our exams. Okay, so looking at our first structure where we have that fused ring system, we've got our benzene here. So you look at what's attached to the benzene. We have an oxygen, and let's go ahead and draw in the lone pairs, and we have a carbon, okay? So we have an alkyl group, or effectively an ether, right? And if you remember from lab, one of the things, and also you're reading in Klein, we talked about the different directing groups, and one general signature of a lot of the ortho-para directors was that there was a lone pair on the atom that was directly attached to the benzene ring. We also saw that our R groups could also be ortho-para directing, but they were weaker donators. So our alkyl group is ortho-para weak director, and then our ether is ortho-para strong. And I think Klein actually classifies things as strong, moderate, and weak. So he has the general classifications and then goes in and kind of further analyzes their strengths. But when we have effectively two substitutions on the ring, the stronger director that's an activator is going to override the positioning of the new functional groups. So if we were trying to do a nitration reaction with this, we would look to the ortho or the para position. And so we have our ortho position here and our para position there. Well, both of those are meta to the alkyl group. So neither one of them has the synergistic effect of you have two directors and they both direct to the same position. So if that's not the case, typically your new functional group will add where there's the most space that's allowed by the directing groups. And so we will probably see our new nitro adding para to the ether that's attached, so directly across from that benzene ring. Now, if we look at the other structure that I picked out from this problem, we now have two benzenes, so there's two options for which ring the nitro could attach, but we've been told it's mononitration, so we're only going to get one nitro on either one of those rings. So if we are looking, we have our carbonyl, that's, if you remember, a meta-director, which is also a deactivator, okay? And then if we draw in our lone pairs, we have an amide that's attached by the nitrogen. That's an ortho-para director, and it's going to be an activator. So once again, our nitrogen that's attached onto the benzene, this amide nitrogen, would be able to direct to the ortho positions or to the para, but especially having this large group attached, it is going to prefer to direct to that para position that we have right here. And so this is where our mononitration is going to be taking place, is para to that amide linkage on the benzene that's directly attached to the nitrogen in the amide. Okay, so moving on, I thought we could probably do with a little bit of practice in terms of directing groups. That was a little bit of a warm-up, and now we've got some where we're just having to draw our final products. So this moves us on to the 6th page of our worksheet, and I thought I would give us an example with the cyano. So if you Remember, CN is cyano, and so it's C triple bond N. And some of you that came to the Wednesday study session this week, we talked a little bit about upcoming chapters, and we have one called carboxylic acids and their derivatives. And our carboxylic acid derivatives can include things like our acid halides that we've talked about, our anhydrides that we saw an example of in the earlier video, also esters and amides, and also it includes your cyano groups because the carbon in the cyano group has the same oxidation state as a carbon that's in a carboxylic acid. And that's kind of the base level description of carboxylic acid derivatives, although most of them do have similar structures to carboxylic acids. So if we have this cyano group, that carbon doesn't have a lone pair on it, okay? And in fact, if you go back through the book or your notes from lab, you'll see that the cyano is a meta director, okay? So that right there is telling us that we're going to attach something at one of those two carbons. And remember, if we got attachment at, for one molecule at the arrow on the top and one for the arrow on the bottom, those are actually the same structure because we have free rotation in space. So we can draw our final product, which should keep our cyano group in place. And then we should put our bromine meta to it. And like I said, the other way we could draw this is identical. So if you don't remember from math, the 3 lines means equal to or identical to, really. And so we only need to draw one of those 2 structures. And hopefully by now we're really comfortable with the fact that bromine and iron tribromide over the arrow will put a bromine onto the benzene. And now hopefully we're getting comfortable with the idea of our meta and orthopara directors. So I thought that would be a good first one to start out with on this page. And then I picked another one. So this is a little bit further up the page. Once again, we have our iron tribromide or catalyst and our bromine. So we're going to be putting a bromine on the benzene. Okay. Now we have a nitro. So it's often common for students to think the nitro doesn't allow Friedel-Crafts alkylation or acylation, so we can't do any reactions with a nitro group when the benzene has a nitro attached. That's not actually the case. Your nitro group is going to be a meta director, okay? And we talked about this in class, how the nitro actually has a positive charge on the nitrogen, and then one of the oxygens has a negative charge on it. But basically, what you have to remember is that the nitro group is just going to cause this to react very, very slowly. So you might heat this reaction up, you might do some other things to help the reaction move forward a little bit faster, but we can put on our halogens and some of our other functional groups if we already have a nitrogen on. We just can't put on our carbon-containing groups because the nitro slows down the kinetics too much. From this page, the last reaction that I thought we could do is the very last one. So here we see ethylbenzene along with this PHCOCl over the arrow. And maybe we don't know what that is, and we need to draw it out, but hopefully we can recognize that catalyst and realize that this might be some kind of Friedel-Crafts reaction. So we talked earlier and reminded ourselves that the pH is just the phenyl, so just the benzene ring, and we've got our chlorine. When we have C and O written out like that in condensed structure, that means that you have a carbon double bonded to an oxygen. And so this structure actually looks like that. Okay? So now that we know what's over the arrow, we can look at our benzene. We have an R group, which is going to be equal to an ortho-para director. So our ethyl is not very big, but probably big enough that your substitution would prefer to attach onto the para position instead of one of the more crowded ortho positions. So let's go ahead and label those to help us keep up with what we're looking at here. So I'm going to draw the major product as this. So we can draw in our carbonyl and then attach on our other benzene, and it will look like that, having those two para to one another. And you could have also just written in the pH for the benzene ring. So I am skipping over the multi-step synthesis because I think that that might be a good thing for us to try in class on Monday. So if you want to give it a shot over the weekend and see what you can come up with, but that's definitely a challenge question. In some ways, it makes you think a little bit beyond just kind of the surface level of all the information. Instead, I'm going to have us move into this nucleophilic aromatic substitution. So this is one of the two other reactions that we get in this chapter. And it's easy to think that it would be labeled NAS, and that would be the abbreviation, but instead we keep the substitution, the nucleophilic substitution trend with an S and then a subscript of N and then an AR for aromatic. Okay. I tried to put in to the worksheets a little bit of information about these, and hopefully you find it helpful. Your nucleophilic aromatic substitutions there's some rules regarding them, and I kind of say, think of this as kind of the flip side of electrophilic aromatic substitution. Your aromatic ring is going to function as an electrophile and something else is going to be a nucleophile. So now, instead of the benzene doing the attacking, a nucleophile is going to attack the benzene ring. So this is going back a little bit more to what we're traditionally used to in terms of the substitution. You can also kind of sum it up as an addition reaction, then an elimination, when you're looking at it kind of as a mechanistic steps, okay? The three criteria in order for nucleophilic aromatic substitution to happen: the ring has to have a very powerful electron withdrawing group attached. Usually that's going to be a nitro group, and Klein really favors the nitro for these examples because they're very powerful electron withdrawing groups. You also have to have a leaving group attached to the ring, and at this point in organic, we should feel pretty comfortable with recognizing leaving groups. I put in a couple that maybe we haven't seen in a while. But basically, your leaving group needs to be able to handle that negative charge that is going to be brought into the ring by the nucleophilic attack, okay? And so I also made a note that while we don't usually see fluoride acting as a leaving group, it can act as a leaving group in these nucleophilic aromatic substitutions. Then the third rule is that the leaving group has to be ortho and para. So if it's not ortho or para, there's a different mechanism happening that we're going to talk about in a minute, okay? So I'm not going to sit here and talk you through the entire mechanism. We can highlight that in class on Monday, but what we can start to do is predict reactions. The only other thing that I would say about the mechanism is you still get a resonance structure that you have to draw out in this mechanism, but it's no longer called the sigma complex or the rhenium ion or the rhenium cation. This is going to be an anion anyways, and it's going to be called the Mesenheimer or the Meisenheimer complex. So it's basically looking the same, but it does have a different term that gets used. If you're reading in your textbook, that's why you're seeing two different names, okay? Now, you're seeing the screen, you see that all of these have step 1 and step 2. Depending upon what nucleophile you're using, you may need a second step in order to protonate the nucleophile, okay? So we're going to kind of talk our way through that as we come across it in our example problems. So the first one, we have a nitro and an iodine attached. So iodine is a good leaving group. Well, let's kind of go through the list of things. And I may have to erase some, but step one, have a nitro group or a very strong electron withdrawing group. We've done that. Step two, have a leaving group. Okay. And we have a leaving group. So nitro leaving group. Okay. And then ortho or para is the third requirement. The iodine is para to the nitro. So we are good to go in terms of identifying this structure as something that would go through a nucleophilic aromatic substitution. Okay. Now, step one includes the nucleophile. It's going to be hydroxide. Okay. It is going to be substituting out for the iodide. That nitro group stays in place. So once you've identified the fact that it is an SNAR reaction, you can draw that nitro group in on your product. It's not changing. Okay. What changes is instead of having an iodine ortho to it, you are now going to have an alcohol ortho to it because the hydroxide is coming in. Okay, if we have our hydroxide attached, that hydrogen that attaches, that's part of the alcohol, part of the phenol, right? Because that's what we've made. We've made 2-nitrophenol at this point. And this OH is protic. It will come off under basic conditions. And of course, sodium hydroxide, the reagent, the nucleophile that we're using is a base, a strong base. So in fact, what we will make initially will look like this. Okay, so a deprotonated form of that phenol, and that's why we use an acidic workup so that we are able to protonate our alkoxide that we're making. And I know the last couple chapters, it seemed like sometimes we use water, sometimes we use acid. Here we can start to kind of clarify we're purposefully using acid when we need a proton donor to protonate our final product and give us a proton source within your aqueous workup. Okay. Again, we can talk about that more on Monday if it's not quite making sense today. So I'm leaving one of these for you to do on your own, but I picked the second one for us to work out in the video. Once again, we see sodium hydroxide over the arrow, so that's going to be what's substituting in. So if we're going through our steps once more, we've got NO2 group, check, that's on our starting material. We have a leaving group. Now, this is not one that we've seen very recently, but this is one of our functional groups, one of those mesylates that will help us to turn our alcohol into a good leaving group. Okay, so having that sulfur with the 2 oxygens, you can picture how the group that I just kind of drew a line between it and the benzene would be a good leaving group because it's going to be resonance stabilized. Okay, so we saw this way back last semester. It's been a while. That's why I wanted us to work through this together. But we do have a leaving group, and then we also have ortho-para. This time our leaving group is para to the nitro group, but like we said before, draw our benzene, draw our nitro, and now we put in our nucleophile in the place where the leaving group used to be. Once again, we're using our H3O plus to work it up because we have basic conditions for our nucleophile. So our proton on the phenol would be deprotonated in step 1 after it's attached, and we need a proton source of weak acid to protonate it in the next step. Our water isn't a strong enough acid to do this protonation. So if you want to, you can draw out your 2 equilibriums with your alkoxide anion and H3O plus versus H2O, just like we did back in chapter, I think it was 3 when we did acids and bases, and figure out which one which reaction will favor the protonation of the alkoxide. But we need H3O plus, not H2O. Okay. The next portion of your worksheet talks about elimination-addition, and that's a very unimaginative name. Literally, you're doing an elimination on the benzene. That's going to create a very weird-looking intermediate that you can see in our slides. And in the book, it's a benzyne intermediate, so it's literally creating a structure that has a triple bond in the benzene ring. And this looks improbable, and for a long time, nobody believed that this was actually an intermediate, but they did radio labeling and verified that, in fact, you were creating this very unstable benzyne with the Y because it's a triple bond. And so we know that this is what's happening now. We've got several examples of mechanisms that we can look at next Monday, but you do an elimination to make the benzyne, and then you do an addition across the triple bond to go back to a double bond and reestablish aromaticity. Okay? So this is the mechanism by which we can do substitutions if you don't have a strong electron withdrawing group on the ring and you don't have two groups, ortho and para, to each other. Okay, and so you'll see in a lot of these examples, they're meta to each other, and this is an allowable reaction. Okay, now benzyne's really hard to make. It's really unstable, so you may notice in the worksheet we're using some really extreme conditions. Liquid ammonia, 350, 200 degrees C. So it's not like this is something that's just easily taking place. You have to be purposefully causing these reactions to occur under very extreme conditions. So one of the last pages of your worksheet has several reactions on it. Some of them are electrophilic aromatic substitutions. Some of them are nucleophilic aromatic substitutions. So what I would encourage you to do as you're solving these, write the products and then really assess which elimination. To me, it's very easy for us to be able to figure out what the products are, but not think about what mechanism it is. So properly, if you look at it, think about what mechanism your molecules could be reacting through, and then write in the products. And for this, I'm going to be writing in all the products. When we make our benzyne, we know that we can add across either carbon, and so we actually do see more products than what we may have been used to seeing with some of our other benzene-containing mechanisms. So when I look at our first problem that I have on the screen here, number one, no nitro group. So right there, we don't have the conditions for an SNAR reaction, okay? We do have a leaving group. So there's our leaving group, our chlorine, okay? They're also not ortho to each other. Those two functional groups are para to one another. However, we do have a nucleophile, okay, our hydroxide. And so we know that our hydroxide is going to substitute out for our chlorine, and we have eliminated the possibility of an SNAR mechanism, the nucleophilic aromatic substitution. Instead, this is going to be an EA mechanism, okay? So one of the products we can draw exactly like we might predict, straight up substitution, okay? The ones that you might not think about are the ones that are a result of the benzyne intermediate. So we actually have two more products that we can draw. One of them is going to look like this. And then we're also going to have a third one where, and you may know where we're going at this point, we're putting our two functional groups ortho to one another. So we've got our meta, and we can also have ortho and para because of the benzyne intermediate and how that could potentially form via the mechanism that we can kind of go through a little bit slower on Monday. If you're looking in your worksheets and you're thinking about this step 2, I do have some examples on when it's appropriate to use water versus acid for step 2 that I kind of put in there in the Elimination-Addition summary that I gave you guys. But once again, we're making a phenol that's going to be a protic proton that would be deprotonated under the reaction conditions in step 1. So we need an acid to act as a proton source and a stronger acid than water in order to protonate our alkoxides we would be making. All right, so looking at the next reaction, we have a different nucleophile finally, okay? It's going to be our amide anion, but let's stop and look at our starting material. We do have a nitro this time, and we do have a leaving group, our chlorine, okay? So once again, let's label that as our leaving group, but they're meta to one another. So because of the positioning, we know that this is going to also be an electrophilic aromatic reaction, or not electrophilic aromatic, an elimination and addition reaction. Okay, so this time we will see our substitution, keeping the nitro, and instead of chlorine, we'll end up with an amine attached to the benzene. So we're making an aniline derivative is really what we're doing here. Just like we saw in the other example, since this is going through the benzyne intermediate, we will also be making the ortho and the para versions of these reactions as well. So you can start to see why these reactions might not be very popular synthetically. You get a mixture of your regioisomers, your constitutional isomers, and you have really extreme conditions to do the reactions in. So you're having to buy special equipment and use a lot of electricity, definitely not green reactions if you're using 350 degrees heat. And then your yield for whichever one of the 3 products you want is pretty low because you're splitting it between 3 potential products. Now, this time, notice step 2 is water. So we put on our NH2, and this is a very strong base, but NH2 is unlikely to get deprotonated to NH with a negative charge on it, okay? So when we're doing our aqueous workup, we want to make sure that what we're doing is going to help protonate things that need protonated, but we don't want to overprotonate, and that's what could happen if we had used our our H3O+. So we know that it's unlikely, but given a strong enough base, we actually will be able to form that NH minus, okay? And so if we're taking just an R group and we have our NH2, okay, it can, using our NH2 minus base, deprotonate and form our nitrogen with a lone pair on it, okay? And so we can make NH minus if we have a strong enough base, and that's why we need water to provide a proton source to reprotonate it. If we used acid instead, remember, we can protonate our amines and turn them into quaternary amines with a positive charge. So that's why when we use amines for our nucleophiles, a lot of times you will see water being used as the aqueous workup so that you don't overprotonate and put a positive charge on the nitrogen. Hopefully that's clear. Since I pre-made our slides and everything, it's a little bit crowded, and I fully recognize that. I'm going to go ahead and erase my little generic acid-base examples, but that's really all that's deciding what is step 2, is going back to, Gen Chem and organic 1, and figuring out which is the appropriate compound to protonate but not overprotonate your final product. Okay, so in this molecule for the starting material, we have a nitro group. So we have a nitro group, we have a leaving group. So remember, our chlorine is a leaving group. And they're ortho and para to one another. So this meets the qualifications for a nucleophilic aromatic substitution, or we can call it SNAR. Okay? So when that's the case, we know we don't really, because of the mechanism, see multiple products. Instead, we get a one-for-one substitution of our nucleophile. Once again, it's hydroxide in this case, for your leaving group. And so we end up making phenol with a nitro group. So p-nitrophenol would be one way to name this, or 2-nitrophenol. Okay. Now, once again, I've included something that's a little bit older leaving group. So we have a leaving group on our structure, but do we have a nitro? No, we don't. Instead, we have a methyl group. So this mechanism is going to be an elimination and an addition. So that means that once again, we're going to see multiple products. One of them most certainly will do the direct substitution. And this time we're using our sodium hydroxide, so it's going to be an alcohol substituting for the leaving group. And then we can also see, in addition to the meta substitution that we have, that we would get ortho as well as a para substitution. And you may have noticed I'm drawing all Robinson structures with the circle in the middle of the benzene ring. This works as long as we're not asked to draw out the mechanism. And since all of these are kind of asking us to draw the final product structures, that's why I keep drawing our rings that way, if you've been wondering why. When we draw our mechanisms, we need to be able to see those pi electrons moving around, and so we have to go back to the Kekulé structures in that case. All right, we have another couple of examples before I've given us some multi-step synthesis towards the very end. So here we have another situation where we need to think, could this be a nucleophilic aromatic substitution or elimination addition? We have the nitro group, criteria 1, we have a leaving group, criteria 2 for SNAR, and they're orthopara to each other. So this is going to be an SNAR. This time our nucleophile is a thiol, and I thought that that would kind of be a good, unusual nucleophile for us to work with. So they put it, I wrote this in, and that's how I've got it in the worksheet too, in our condensed structure. We can draw it in our bond line structure though, and we see our sulfur nucleophile substituting in for our iodide, or our iodine leaving group. All right, the last one I thought I would work through the fused ring system that's on the back of that next to last page in the worksheet. Really, we don't have to worry a lot about the cyclohexane that's attached, okay? Instead, we're focusing on the benzene ring, okay? So technically, we have substitutions at every position on this ring. We've got 2 R groups, 2 fluorines, a nitro. The only position that's available, if we were trying to add anything new, would be that position right next to the nitro. So if we're looking, we have a nitro group, we have 2 leaving groups, and one of them, the fluorine that's para, is in the ortho-para position. So this actually qualifies as a nucleophilic aromatic substitution reaction. Nothing happens with our cyclohexane, like I said, so we can draw it in. Our nitro group stays in place. Nothing happens with the metafluorine. And we can draw our substitution for the hydroxide, substituting in for the fluorine. And that's going to be our product. We don't really have very extreme conditions in order to be able to do our electrophilic, or rather our elimination-addition, our EA reaction conditions. And certainly thinking about the intermediates, it is a little faster kinetically to do the SNAR versus the EA. So the nucleophilic aromatic substitution would be preferred versus the elimination addition with the benzyne intermediate. Okay, I've got two multi-step problems, and I'm leaving you the two that are actually on the worksheet. I came up with two more for us to practice, so you get a little bit more practice. So we want to go from a benzene to something that has an isopropyl group and a chlorine attached. When we're thinking about these problems, we have to think about ortho-para directors, okay? And of course, meta directors. So one thing you might start doing is kind of writing down, you want your two substituents to be ortho to one another. And when we look at them, both of them are ortho-para directors, okay? Generally speaking, if you have two ortho-para directors, maybe put on the activator first, because then the reactions will go a little bit faster. And in that case, we'll try to put on our alkyl group first, because that's the activator. Your chlorine is ortho-para, but remember, it's a deactivator. So I'll go ahead and write these labels in for us to help us remember. You certainly don't have to show all this work when you're solving your own multi-step syntheses. And with ortho-para directors, we have to think about it. We're doing ortho, but what about that para position? We learned something earlier that we could put in effectively, I think Klein's calling it a blocking group, but it's a protecting group to protect that carbon from being reacted when you have an ortho-para director attached to the ring. So first step, let's put on our isopropyl group. So that's going to be a Friedel-Crafts acylation reaction. Luckily, because of the structure, we don't have to worry about any kind of rearrangements. And so we get that product in pretty good yields. Now we're going to want to put in a blocking group. If we tried to introduce the chlorine now, we would get a lot of para substitution and some ortho substitution. But the isopropyl is bulky enough, para would be the major product. So let's be a little more cautious and a little more careful in our chemistry and put in a blocking group instead of just taking the loss on our percent yield. So here's my isopropyl, and that's our reaction conditions for putting on that sulfonyl group. And actually, I should write this the way that it would appear. So remember, your bonding kind of matters. So we always want the sulfur to be attached onto the carbon, even if it makes drawing out what your reagents are or what your functional group is a little bulky. So now the next thing we can do is put on our chlorine. Now it has no choice but to go to the ortho position. So we end up with a structure that has the isopropyl. It still has the SO3H, and now it also has a chlorine. Hopefully you remember that to remove that SO3H group, we just need to use dilute sulfuric acid, and that will give us our final product. And I'll go in here, erase what we were talking about with the ortho position. to give us our final product. So on a test, you're welcome to use, if I give you a starting material and a final product, you're welcome to kind of draw them in this loop format for multi-step, or you could just redraw everything underneath. I typically give you enough space to do either one. All right, last multi-step synthesis. So once again, two functional groups, ortho to one another. Okay, so let's make that note. Ortho. You have a bulky group, the terp butyl. And so if we're putting on the terp butyl group, we know the bromine would prefer to go to the less bulky, the less sterically strained area in the para position. So you're going to want to put on your activator first, and then your deactivator. But you also need to put in a protecting or blocking group. Okay, so once again, Friedel-Crafts alkylation will be first, and a lot of times, I'm not saying that every multi-step is always doing a Friedel-Crafts alkylation. Certainly we'll see some acylations and other reactions being used, but that is the reaction that we have to watch out for, having a nitro group on the ring. So a lot of times, especially if there's going to be a nitro group on it eventually, you see the Friedel-Crafts reactions being done first. So after the acylation, we end up with a terp butyl group attached. This is now where we will do our blocking. So concentrated fuming, sulfuric acid, and that's a big group, so it will add para. I'm going to erase my really big sulfuric acid over the arrow and redraw it. Okay. Now we can do our bromination this time, Br2 with iron tribromide. Or, we haven't used it much this time, it could have been aluminum tribromide. Okay. So that will give us the structure with our bromine attached. And then the only thing that we need to do is take off that blocking group, as Klein's calling the SO3H. And so we do that by using dilute sulfuric acid. Okay. If you have any questions, feel free to email me or send me a message, and we will recap over Chapter 18, the first half of class probably on Monday, and then the second half of class, we maybe start at 19. Like I said in the email, we won't be able to get all the way through 19.5. That's a very long section. But we can start to get a feel for Chapter 19, reactions with aldehydes and ketones. We've already seen a lot of how the mechanism works. We're just going to kind of explore from a different aspect. So this is one of those where Klein's kind of reiterating some of the things that we've already learned.